Hello, Professor. We could start.
Okay, thank you. Let's start. Let me switch off my video as usual. We'll continue with the example which I discussed at the end of the previous lecture. The example of the reductive group G itself, considered as a spherical homogeneous space under the double group G cross G. G cross G modulo the diagonal. We already described the weight lattice and the evaluation cone for this spherical homogeneous space. Let me recall that the weight lattice in this case can be identified with the character lattice of the maximal torus in G, and it is embedded in the character lattice of the maximal torus in G cross G, that is in T cross T, in the character lattice of T cross T, in the anti-diagonal way, that is the character lambda is mapped to the pair minus lambda and lambda. So this is a weight lattice, and under this identification, the evaluation cone for this spherical homogeneous space is identified with the negative Wild chamber in the vector space spanned by the dual lattice. That is, it is the set of all vectors V in the vector space spanned by the dual lattice. Such that they take non-positive values on all simple roots. So alpha i's are denoting simple roots of G. This was the description of the evaluation cone, and it remains to describe the colors. The description of colors can be deduced from the Brouillard decomposition in G. Brouillard decomposition. The Brouillard decomposition is the decomposition of G into the union of double cosets for the Borel subgroup, or maybe for a pair of different Borel subgroups, which will be more convenient in our situation. It is a classical thing in the structure theory of reductive groups, and it is described, for instance, let me give you references. It is described, for instance, in the book of Humphrey. Linear algebraic groups in the section 29. Another good reference is the book of Springer, Tony Springer, which I also mentioned in the reference list. The title of the book is the same, Linear Algebraic Groups. And the Brouillard decomposition is discussed there in the section section 8, chapter 8 and section 3. So the section is 8.3. Actually, we don't need the Breuer decomposition in full generality. We only need the description of prime divisors in the complement of the big cell that are exactly the colors in our situation. And the description is as follows. So each color, there are as many colors as many are the simple roots. And each color is the closure of the double coset b minus dot r sub I dot b, the closure of this double coset. So I ranges from 1 to L. And these RIs are what are called simple reflections. Simple reflections. These elements Ri are called simple reflections. Let me recall what are simple reflections. Maybe I should better turn to the next page. So for each simple root, we have a three-dimensional simple Lie subalgebra in G, in the Lie algebra of G. Let me denote it as...
I want to see the last page about the name of the simple reflections.
Simple reflections. Yes.
I think I have seen reflections in the definition of well group. Right.
They are, yeah. You will see immediately in a couple of minutes that these are the same. These are the same things. Well, up to some abuse of language. You'll see it in a moment, okay? So for each simple root alpha I, let us consider the three-dimensional subalgebra Si. So this German S sub I denotes the three-dimensional simple subalgebra, simple Lie subalgebra, spanned by the following three elements. So the root vector E sub alpha I, the root vector corresponding to the opposite root E sub minus alpha I, and their commutator. So these three elements in the Lie algebra of G span a three-dimensional Lie subalgebra, which is actually isomorphic to the Lie algebra SL2. And under this isomorphism, the root vector E alpha I corresponds to the matrix of this form, 0, 1, 0, 0. The root vector E sub minus alpha I corresponds to the matrix of this form, 0, 0, 1, 0. And their commutator is the diagonal matrix, 1, 0, 0, minus 1. So these three matrices form the standard basis of the Lie algebra SL2. And this three-dimensional Lie subalgebra Si is isomorphic to SL2. So
what is the character for this subalgebra, Y or G? The character is
say it again.
Well, which character do you use to describe this subalgebra? Yi or Gi or something?
So you mean this character?
Yes.
This is a German S, small letter S in German
And what about the first character?
The first character? You mean this?
This is yes.
This is G. This is German G.
I know.
This is the Lie algebra of big G, the Lie algebra of my reductive group G. So as usual, this is our usual convention that we denote the Lie algebras of algebraic groups by the same letters, but small letters and in German writing. Okay, so to this simple three-dimensional Lie subalgebra Si, there corresponds a three-dimensional algebraic subgroup, which I denote by capital Si. So our G contains the three-dimensional algebraic subgroup Si, which is isomorphic either to SL2, the group SL2, or PSL2. So the Lie algebra will be the same, but the group may differ. It is either SL2 or SL2 modulo its center, modulo the finite subgroup of order 2. Okay? So, and now what is this simple reflection, this Ri? This element Ri is actually an element in this three-dimensional algebraic subgroup Si, corresponding under this isomorphism, corresponding to a matrix of this form: 0, 1, minus 1, 0. This is what I call the simple reflection Ri. Well, strictly speaking, the simple reflections are not these elements in the three-dimensional subgroups, but simple reflections are their cosets modulo the maximal torus of G. That is, they are elements of the Weil group. But we'll not make this distinction just by abuse of language. We call these elements also simple reflections. So for our purposes, this will be okay. So we get the description. Let me come back to the previous page. We get this description of colors, the prime divisors in the complement of the big cell of the B minus cross B open orbit in G, as closures of double cosets containing simple reflections. Okay, this stems from the Brouillard decomposition, which I will not explain in detail, so I give you this reference for further reading. Now, what I want to do, finally, we shall compute the map from the set of colors, which we just described, to the dual weight lattice, to the dual of the weight lattice. Let's consider any B semi-invariant, B minus cross B semi-invariant function on G. This is the function of some eigenweight minus lambda comma lambda. We have described these functions on the previous lecture. And what I want to do, I want to compute the vanishing order of this function along any of the colors. So I want to compute this vanishing order. Actually, I can do it in the following way. This vanishing order equals the vanishing order of this function f restricted on a curve in my group G, a curve G of t, which belongs to the big cell, to the open Borel orbit, for all values of the parameter t except 0. And when t is equal to 0, then this curve G of t passes through this element Ri, and it is transversal to the color di. Excuse me. Transversal to di. At this point, G of 0, which is equal to Ri. So let me draw a picture for you. We have our group G. This is our group G. We have this color di. We have an element, a point Ri in the open Borel orbit on this divisor. The point Ri. And we have this curve G of t meeting this divisor transversally at this point. So I claim that the vanishing order of f along this divisor di is just the vanishing order of this function of the parameter t at the value of t equal to 0. Okay. Clearly, this is true if g of t were a general curve transversal to this divisor. But since this curve g of t meets this divisor at a point in the open Borel orbit, and the function whose vanishing order we are computing is b minus cross b semi-invariant, then the vanishing order at this point will be the same as the vanishing order at any other point of the curve shifted by the action of the Borel subgroup. So the vanishing order at a general of this function at a general curve transversal to this divisor will be the same. This is for this reason it suffices to compute the vanishing order at this particular curve. Okay. Now, how to do it? How to compute this vanishing order? Again, we shall use the Brouillard decomposition. It follows from the Brouillard decomposition that G contains an open subset which is slightly bigger than the big cell. The open subset of the following form. It is a product of several subgroups. Ni minus dot Si, which we have seen above, dot Ti dot Ni plus. So these subgroups are the following. So Ni minus and Ni plus, Ni plus or minus, are the unipotent subgroups which are exponential images of the Lie subalgebras composed from the root subspaces. So you have to take the direct sum of all root subspaces corresponding either to positive or negative roots alpha plus or minus alpha, where alpha ranges over all positive roots except the simple root alpha I. So you take all positive roots except alpha I. You take the direct sum of all root subspaces. This will be the codimension 1 Lie subalgebra in the Lie algebra of the maximal unipotent subgroup. And then you take the exponential of this Lie subalgebra. You get a codimension 1 unipotent subgroup in U plus or in U minus. U plus is the unipotent part of B, and U minus is the unipotent part of B minus. So these are these unipotent subgroups on the left and on the right. And Ti is a codimension 1 subtorus in T. Codimension 1 subtorus in T, complementary to the maximal torus of this Si. So Si, recall that Si is isomorphic to SL2 or PSL2. And the maximal torus in SL2 or PSL2 is just given by diagonal matrices with determinant 1. So we get a one-dimensional subtorus in G or in T also, and this Ti is the codimensional subtorus complementary to this one-dimensional torus that is such that their direct product will be T, will be the whole T. So as I said, it follows from the Brouillard decomposition that G contains this open subset. This open subset in ni minus dot si dot ti dot ni plus contains the big cell, of course, because si contains the root subgroups corresponding to alpha I and alpha and minus alpha I. So we get all root subgroups here, and also we get the whole torus T, which is the product of the maximal torus in Si and this Ti. So this product set on the right contains the big cell, but it also intersects the color Di. So this color Di, which we are considering, intersects this open subset. Let me maybe write here that it is an open subset. Open subset. The color Di intersects this open subset in the following set. It is again a product. Yes.
I want to see the matrix representation of the simple reflection Ri. I want to check. Well, I don't think. No. I understand now. The matrix of Ri is in the Lie algebra, not in the Lie group.
No. The matrix of Ri is in the Lie group. Is in the algebraic group Si. So the matrix is
this group 0 minus 1 minus 1 0 does not have determinant 1.
It does. Of course it does.
I didn't see clearly. Thanks.
Okay, now it's clear. Yeah. Okay, let's go on. So as I said, the divisor Di intersects this open product subset in the following set: Ni minus times Di intersect with Si times Ti times Ni plus. So this is the open subset, which is the intersection of Di with this open subset in G, with the above open subset in G. And this intersection of Di with Si is just the set of matrices of this form. You have 0 here, you have something here, and something here. This is the intersection of the color Di with this three-dimensional subgroup Si. So we want to compute this vanishing order. So we want to choose this curve G of T, which intersects Di transversally at this point Ri. Let's take the following curve. So let's take this curve G of T belonging to the subgroup Si, which is isomorphic to SL2 or PSL2. And in this matrix presentation, this curve will be given by the matrices of this form. We understand this matrix as an element in Si, which is isomorphic to SL2 or PSL2. So you see clear? Yes.
Why is Di containing the product of the four elements?
Well, because Di is stable under the action of B minus on the left and B plus on the right. And this
Yes.
Ni minus is contained in B minus, while Ni plus is contained in B plus. Okay.
This does not mean that the right-hand side is an open subset in DI, right?
This means, of course, I claim this, but well, let me say that I do not prove this statement in detail, because I assume that it follows from the Breuer decomposition, from the analysis of the Breuer decomposition. I just give you a clue how it looks, but to understand this in more details, you have to go through Breuer decomposition. So I claim that indeed this, well, but by the way, it's more or less clear that the how to say, that this set, excuse me, that this set is open in DI because what is this set on the right? Actually, it contains the double coset. It contains this double coset whose closure is DI. Because this intersection DI with SI contains the element RI. This element, yeah? This element is contained in this intersection, clearly. And when you act by B minus on the left and by B plus on the right, you get these products, actually. So the action of T is both on the left and on the right. You can write it from this side, for instance. And here you get the action of U minus, because the action of the root subgroup corresponding to minus alpha I is already in here. It is already counted in here. So this guy is stable under the left translation of the root subgroup corresponding to minus alpha I. So it remains to translate by this guy, and this we do. And on the right, it remains to translate by this guy. So finally, we see that the whole coset B minus Ri B plus is contained in this product set. And this means that it is open in DI, okay? So this indeed can be explained without going deeper into Breuer decomposition. But let me come back to computing the vanishing order. So let us take this curve in SI. Clearly, it intersects the divisor DI transversally at the point Ri when t equals to 0. So when t equals to 0, we get exactly the element Ri. And the whole curve is intersecting this set transversally. So this curve, g of t, suits for our purpose. And we can rewrite this curve a bit differently, like the product of matrices of the following form. So let me just write it, and you easily check that this equality is true. 1, 0, minus t inverse 1 times t 0, 0, t inverse times 1 t inverse 0, 1. So you easily check that this product of the three matrices equals to g of t, equals to this matrix. I will skip this checking. But this is in the language of matrices, in the language of SL2. And in the language of this group SI sitting in G, this can be written as follows. This is the same as. So the first matrix is the exponential of minus t inverse times the root vector E minus alpha I. The second matrix, depending on t, on the multiplicative parameter t, is just the one parameter subgroup corresponding to the maximal torus of SI. It is one dimensional. And this one parameter subgroup is given by some vector in the dual of the character lattice, which is denoted alpha I check. So this alpha I check is a vector in the dual of the character lattice called the simple co-root corresponding to the simple root alpha I. So it is the simple co-root corresponding to alpha I. So you can read more about simple co-roots, simple roots, and simple co-roots in the references. Yes, yes.
If it is a co-root, then it should send the element t. It should send the element t or the character t to a rational number. Well, what is the rational number it sends to?
Well, let me write in more details. So so the value of this alpha I check, well, say the value of alpha I check at any other simple root alpha j first. It is what is called the Cartan number. Cartan number. So Cartan numbers occur in the properties of the root system, of root systems. And there are some integer numbers, non-positive, unless I equals to j. And when I equals to j, this Cartan number is 2. So there are certain axioms about these Cartan numbers. I will not mention them now. But let me just give you a couple of references for this type of things. What are simple roots, simple co-roots?
I'm not saying that. I'm saying well, the t alpha I has
well, this notation.
This notation is not alpha I has acting on t.
This notation, let me say, this notation we have already used. If t is a multiplicative parameter, and we have some vector in the dual character lattice, then there is a well-defined multiplicative one-parameter subgroup corresponding to this dual character, to this co-character. And this one-parameter subgroup was denoted like this. We already used this notation. T to some power, where t is the multiplicative parameter, and the power is a co-character. So we use this notation when we proved the finiteness theorem. We considered some limits on the one-parameter subgroups. So just look at this notation there. So this is just the notation for a one-parameter subgroup corresponding to a co-character. And what is this co-character? Let me just give you a couple of references about simple co-roots. It is some co-character. I don't want to explain what is it explicitly, but you can look in the following books. So, for instance, in Onishik and Winberg, the same book which I already mentioned, Onishik and Winberg, Lie groups and algebraic groups. Chapter 4 and paragraph 2.
Well, when you say finiteness, the finiteness theorem, it is about the finiteness of the G orbit in a spherical variety, right? Or some other finiteness. theorem?
It is the second finiteness theorem, the theorem of Ahiezer, saying that if you have a homogeneous space such that if you have a homogeneous space such that all its embeddings have finitely many orbits, then this homogeneous space is spherical. In the course of proving this theorem, we can see that some limits of point in projective varieties under the action of multiplicative one-parameter subgroups. Just look at the proof and you will see it there. And when we discussed these multiplicative one-parameter subgroups, we introduced this notation. Okay, so this is not more than just notation.
I see the notation now.
Okay. So let me also give you the second reference. This is the book of Springer, which I already mentioned today. It is even maybe more relevant to this situation. The book of Springer, linear algebraic groups. So the section 7.4. In this section, let me just finish. In this section, there are discussed the root data corresponding to reductive groups. So there is a notion of root data. And these simple roots and simple co-roots are coming from this root data. Okay? Yeah.
But Professor, I think when we define, when we use this notation, the gamma, the character in the exponent is from the character lattice of T, not the dual of the lattice, I think.
No, the co-root is in the dual of the character lattice. The root
but when we write something in the exponent to define multiplicative subgroup, then the exponent should come from the character lattice. I think in that class we define like this, not in the
no. Well, maybe let's take a look. I don't remember what was this lecture 7 maybe. No, it was not lecture 7. Lecture maybe this one. Yeah, finiteness theorems. So maybe the next.
Yes, you are right. I didn't look into my notes.
Okay. So now you agree, but let me check that I have written everything correctly. I think that it was, so you see, it is here. So here you take gamma in the dual of the character lattice. Okay.
Yes. I see that.
Okay. So this is this notation from lecture 8 or 9. What was this? Lecture 9. Yeah. So this notation from lecture 9 describes this power notation for one-parameter multiplicative subgroups. Let's come back to our lecture, to our current lecture. So let me finish rewriting the presentation for this curve G of T, because I didn't yet finish. I rewrote the factor in the middle, T0, T inverse, as this multiplicative one-parameter subgroup. And finally, the last factor on the right can be rewritten as exponential of T inverse times the root vector E alpha I. So this is the presentation of G of T in the big cell. So this is in this product U minus dot T dot U, or U plus if you like. The presentation of G of T in the big cell of G for non-zero values of the parameter. And now it remains to compute to compute the value of my function f, this function f of eigenweight minus lambda lambda, at this curve. Let's do it. So we have so it follows from the previous formula that the value of f at g of t is the same as the value of f at the middle term t to the power alpha I check, because the terms on the left and on the right belong to u minus and u respectively, and f is semi-invariant under b minus across b. That means that it is invariant under u minus and u, because all characters take value 1 on unipotent parts of b minus and b. So it remains to compute f, the value of f on this multiplicative one-parameter subgroup in the middle. And we have already did it at the previous lecture. It is the same as the value of the character, lambda at this multiplicative one-parameter subgroup. That is t to the power.
I have a question about for the b minus times b action on f. I think we multiply the b minus part, but b minus element to the right of the variable.
No. B minus was on the left. B minus was on the left.
B minus on the left acting on f, but not acting on the variable of f.
But not acting on what?
The variable of f. B minus acting on the left of f.
Let me show you. Let me show you this action. So b minus was acting on the left, and b was acting on the right, and this is a big cell. And when we compute,
I see now.
Okay, good. Then let's go back to what we are doing now. So it follows from the formula you have just seen from the previous lecture, that the value of our function f of eigenweight minus lambda lambda at this g of t can be computed like this. And this means, so hence, this means that the color di is represented in the dual of the weight lattice. So in our notation, the color di is represented by the vector v bar sub di. This vector is just the dual, the simple coroot alpha I check, because the value of this vector in the dual lattice on each weight lambda is the same as the value of the respective valuation on the function f of eigenweight minus lambda lambda. So the formula on the first line on this page shows that the colors are represented by simple coroots on the weight lattice. So the whole picture looks like this. You have the root system, or maybe better to say, you should consider the coroots corresponding to the root system. Let me give you, for example, draw the root system of type A2, the root system of SL3. So this is the root system. All roots, positive and negative. Okay. You have simple coroot. So this is not the root system, but the coroot system. So these vectors represent coroots in the dual lattice. And we have simple coroots, which are these two in this example. So this is alpha 1 and alpha 2. So these are simple coroots, alpha I check. They represent the colors. And the valuation cone is the negative Weil chamber corresponding to this simple coroots. That is the cone which is negative dual to the cone spanned by simple roots. Let me draw it on the picture. So the valuation cone is this negative Weil chamber. Like this. So this is the valuation cone. This is V sub G. Again, let me repeat that in this example, the color data sit in the space spanned by the co-character lattice of the maximal torus of G, so that the valuation cone is the negative Weil chamber, and the colors are represented by the simple coroots. So this is the picture in this particular example. And in general, morally, you should think of the valuation cone as the analog of the negative Weil chamber, and of colors as analogs of simple coroots. In fact, the valuation cone is a strict analog of the negative Weil chamber in the sense that there exists a root system sitting in the dual of the weight lattice, such that the valuation cone is exactly the negative Weil chamber for this root system. And as for colors, they are analogs of simple coroots in a weaker way. So they do not correspond to simple coroots of this special root system. This is just somewhat different set. But anyway, morally, you should imagine a picture like this. When you consider the color data of a spherical homogeneous space, you should keep in mind a picture like this. So the valuation cone looks somewhat like the negative Weil chamber, and colors look at this picture somewhat like simple coroots. Okay? Let me finish the first part of my lecture by giving you an exercise. So we computed the color data for the group G itself, considered as a spherical homogeneous space under G cross G. And now try to compute the color data. Compute the color data. The color data for the following spherical homogeneous spaces. The generalized flag variety G mod B, and also the quotient space G mod U, modulo the maximal unipotent subgroup of G. The computation here can be somehow reduced to the example which we just computed, but just try to do it. So let me finish the first half of my lecture at this point. If you have any questions on the first half of the lecture and any other questions, then I am ready to answer. Okay.
Professor, I want to ask about the intersection of DI and SI.
Okay, so I guess it is here, right?
Yes. Well, is it true that the intersection of DI and SI is SI times RI times SI? Well, the double SI action on the simple reflection.
This intersection is the double coset. This intersection is the double coset of the same form. But now you have to take B and B minus to be the Borel subgroups in SI, not in the whole G.
Borel subgroup in SI. Oh.
Yeah. So let me write it explicitly, maybe. So this guy is the same as B minus intersect with SI times RI times B intersect with SI. Okay. So the intersection of B minus with SI is just the group of lower triangular matrices in SL2. So you have something here, and something here, and zero here. This is this intersection. So what is Ri? We have already seen. It is this matrix. And the intersection on the right is the Borel subgroup of upper triangular matrices. So you have something here, something here, something here, and zero here. This is this intersection.
Well,
and the product.
I know this product definitely contained in the intersection. And I want to ask, why isn't there possibility that we multiply Ri by two elements that is not in SI, but the result is in SI?
You mean when you multiply Ri by something from here or from here and get in here?
Yes.
Well, actually, this I skip, but actually it is true that this product is a direct product of varieties. So this decomposition is unique. If you have an element G sitting in here, then it is uniquely decomposed as a product of something from here, from here, from here, and from here. This again stems from the Brouillard decomposition. I just brushed it under the carpet because I don't have time to go so deeply in details of the Brouillard decomposition. But it is true, yes, it is true that this product is direct product not of groups but of varieties. This decomposition is unique. Okay. So, more questions, if you have any. Well, if there are no more questions for the moment, I just turn off my microphone. But I'm still here, and if you have some questions, if some questions arise, then just ask me. I will switch on my microphone again and answer. Okay. Now we still have 6 minutes of the break. Okay, let's continue. Let's go on with the lecture. Now we are ready to build up the classification of spherical varieties. Recall that we are studying the following classification problem. To classify all normal spherical varieties containing a given spherical homogeneous space as the open orbit. So the spherical varieties X should contain a given spherical homogeneous space, Y not, as the open orbit. So this embedding should be an open embedding. Actually, we consider only normal varieties, so I put this word normal in brackets. I'll just speak about spherical varieties, assuming they are normal by default. So since we have fixed the open orbit, we have fixed the color data, which are birational invariants of a spherical variety. So the color data are fixed. What are the color data? The weight lattice, lambda, the evaluation cone V sitting in the space spanned by the dual lattice lambda star, and the set of colors, it is a finite set, equipped with a map in the dual of the weight lattice. So this triple is, or maybe quadruple, if you also consider this map as an element of the data. So this triple or quadruple will be denoted by dropping the subscript x, because for all x under consideration, the color data will be the same. So I just drop the subscript, which I have written before. I just write lambda instead of lambda x, v instead of v sub x, and d instead of d sub x. Okay? So the idea to classify spherical varieties with a given open orbit is to do it by some combinatorial data cooked up from the color data of the open orbit. To do this, let us recall first that any spherical variety contains finitely many G orbits. Finitely many G orbits. Say yi, where I ranges over some finite set of indices. And now for any G orbit, say y in x, let us denote by x sub y the set of all points in x such that their orbit closures contain y. So essentially we take the union of all orbits containing y in their closures. This is x sub y. In other words, x sub I can be expressed by removing from x the union of all orbit closures yi bar which do not contain y. Which do not contain y. And since there are finitely many orbits y sub I, there are finitely many their closures, which are closed subsets in X. And when we remove from X the union of finitely many closed subsets, we get something open. So this X sub Y is open in X. Okay? And also, X sub Y contains the orbit Y as the unique closed G orbit. So the orbit Y is the unique closed unique G orbit. Let me write it like this, unique G orbit, which is closed in this subset. It may be non-closed in X, but it is closed in X sub Y. Just because by definition all other G orbits in X sub I contain Y in their closures. So Y is the unique closed G orbit in X sub Y. Okay? And finally, let us remark that the whole X is the union of finitely many such open subsets. So the whole X is the union of X sub Y over all orbits Y in X. So it is a finite open cover of X. Okay? So to summarize, we have covered our spherical variety X by finitely many G-stable open subvarieties, each of them containing a unique closed orbit. Such a spherical variety containing a unique closed orbit is called simple. Let me write the definition. So definition: a spherical variety X is called simple if it contains a unique closed orbit. So we have covered X by finitely many simple open subvarieties. And therefore, our classification problem subdivides into the two subproblems. So the first problem, problem 1, is to classify first simple spherical varieties. And then the second problem is how to glue them together to obtain arbitrary spherical varieties. Since we already know that any spherical variety is covered by finitely many simple open subvarieties, and we know how to classify them, how to describe them, the remaining question, the last question, is to how to glue them together to obtain the whole spherical variety X. Okay? So we'll solve both problems, but first we start with the first problem. So now let us suppose that our variety x is simple. Suppose for a while that our variety x is simple.
Well, simple means X is already a spherical variety, right?
Yes, yes. Well, you may give a definition in bigger generality, but for me it suffices to consider all the spherical varieties. So for me, simple is automatically spherical. Yes, yes. Of course, the definition can be generalized, but I don't need it. So suppose X is a simple spherical variety, and let me denote by Y the unique closed orbit in X. So that in our notation, X can be written as X sub Y. All orbits in X contain Y in the enclosure. So X is the same as X sub Y in the previous notation. The first statement which I'll prove about spherical varieties, about simple spherical varieties, is quite easy. So proposition, it says that simple spherical varieties are always quasi-projective. Why so? It stems from the Sumihiro theorem. So Sumihiro theorem, the Sumihiro theorem says that any point in X has a G-stable quasi-projective open neighborhood. And if we take a point in the closed orbit, then the quasi-projective G-stable open neighborhood of this point will contain the whole orbit. So Sumihiro's theorem implies that there exists a G-stable quasi-projective open subset, say X not in X, containing the closed orbit Y. So let me draw it at the picture. You have your X. You have your closed orbit Y. And you have a quasi-projective open neighborhood X naught containing Y. But if you take any point outside this X naught, so if you take any point in the complement, it is a closed subset of X, G-stable closed subset of X, then we immediately get that the closure of the orbit of this point still still is contained in this complement because it is closed. And therefore, it does not intersect Y. But this is a contradiction. This cannot happen because Y is a unique closed orbit, and it should be contained in any other orbit closure. So this means that, so since X is simple, and there is a unique closed orbit, this implies that it just has to coincide with X naught. Therefore, X itself is quasi-projective, and we are done. We have proved the claim.
Professor, I have a question.
Yes.
You mean that Y is a unique closed orbit. So how can we deduce from that every closure of orbit should contain Y?
Because in the orbit closure there exists a closed orbit sitting in the orbit closure of any other orbit. So the
closed orbit in the orbit closure is defined from what?
Well, for instance, you may take the orbit of minimal dimension in the orbit closure. It is automatically closed because all orbits in its closure should have the smaller dimension. And if you take the orbit of minimal dimension, it is automatically closed. Okay?
So we can always choose a closed orbit from a closed G-stable subset, right?
Exactly. Any closed G-stable subset contains a closed orbit. For instance, any orbit of minimal dimension in this subset will be closed. Okay? Okay. So we have proved that all simple spherical varieties are quasi-projective. Now let's go on. So our aim is to classify simple spherical varieties. Let us consider the following data related to a simple spherical variety. So essentially, we'll consider all b-stable prime divisor on X containing Y. All b-stable prime divisors on this simple spherical variety X containing the closed orbit Y. These divisors can be of two types: G-stable divisors and colors. So we have two types of data. So the first one is the set, which I denote as follows: V upper Y. It is the set of all G invariant valuations corresponding to G stable prime divisors in X. Since I am assuming X to be simple, any G stable prime divisor should contain Y. But let me write it explicitly that these divisors contain Y, because I can define actually this set not only in the simple case, but for any spherical variety. Just consider the set of all G-stable prime divisors containing a given G orbit. This is the same thing. So the respective valuations are some vectors in the valuation column. So we get a finite subset in the valuation column, denoted V over Y. The second set, denoted D over Y, is the set of colors with the same property. The set of all colors, D in script D, containing the closed G orbit Y. It is some finite subset of colors. And finally, let me denote by X, Y over naught, upper naught, the complement in my spherical variety, in my simple spherical variety XY, the complement of the union of remaining colors. So we remove all colors which do not contain Y in their closure. All colors D sitting outside this subset, D over Y. So let me draw it on the picture, what we are doing. So we have this x. Well, again, I mean, you may use the same pictures as above on the same page, but let me draw a separate picture because I don't want to put too much on this first picture. It was for the proof of the previous proposition. So, so we have this x. We have this x. We have the orbit y, the closed orbit y in x. And we remove all colors which do not contain y. So we remove all colors of this form. Maybe this one. Or this one. So these colors which do not contain y are removed. These d's. This blue d and yellow d are removed. And what is left is an open subset, which I denote x, y, naught. Okay, this is the picture for this open subset. Now the first lemma, which I need.
Professor, I want to see the picture again. Oh.
Okay. So you see what happens. You just remove all colors which do not contain y, Okay. And what is left is some open subset. Okay. So let me then turn to the next page, if you don't mind. So the first lemma I need is the following. I claim that this open subset x, y, upper naught is the smallest by inclusion, B-stable, affine open subset intersecting the closed orbit y.
Smallest in x, right?
Smallest, yes, smallest in x by inclusion. Smallest by inclusion among open subsets, among B-stable open subsets in x intersecting y. Among B-stable affine open subsets in x intersecting y. We already see from the definition that it is open. We want to prove that it is affine. It is an affine variety, and we want to prove that it contains any other affine variety. It is contained in any other affine open subvariety intersecting y. Okay. And also, in addition to this statement, is the description of the coordinate algebra of this affine open subset. So, by the way, sometimes this open subset is called the canonical open B chart of X. So let me use this name in the sequel. So this is the of Y. I'm sorry, the canonical open B chart. So open B chart of the orbit Y. This is the name for this open subset. Okay, and some addition to this lemma, a small addition to this lemma says that the coordinate algebra of this open B chart consists of all functions which are regular on the open B orbit. It was previously denoted by y upper naught, the open B orbit, such that the evaluations corresponding to these two subsets, v over y and d over y, are non-negative at this function. So let me write it down here. So v of f is non-negative, and vd of f is non-negative for any v in v over y and any d in d over y. Okay, so this is the description of the coordinate algebra of this affine open subset. Actually, this description is more or less obvious, but let me postpone it for a while. So now I have to prove this lemma, but I'm just thinking what is better to do, either to prove this lemma or...
We do not prove the proposition, right?
Excuse me? As for the proposition, we already proved it. We proved the proposition. So this lemma is not needed to prove the proposition. The proof of the proposition was finished here.
Oh, I mean the proposition, or I mean the description of the regular function on x, y naught.
Ah, this description. Well, this description is easy. You just well, let me say a few words. I will come back to it later, but let me say a few words now. So since this affine variety x, y naught is normal, a function is regular on it if and only if it has no poles. What can be the poles here? So if you want to have a regular function, then first this function should be regular on the open orbit, on the open B orbit, sitting in this chart. Because this chart contains, of course, the open B orbit, y upper naught. So first, a function should be regular on this open orbit. And in the complement of this open orbit, there sits B-stable prime divisors. B-stable prime divisors sitting in this x, y naught, in the complement of y naught. Okay? So these B-stable prime divisors are exactly the divisors from these two sets. So these B-stable prime divisors are either these divisors or these divisors. Because we removed all other colors. We removed all colors not containing y. So what is left?
So the d upper y, the divisor in d upper y is not required to be g-stable, right?
No, the divisors in d upper y are b-stable, but not g-stable. They are colors.
B-stable, yes, it's colors.
These divisors are only b-stable, and these divisors are g-stable. Divisors corresponding to this set are g-stable. So these divisors intersect this open chart, this open affine chart. And the divisors not belonging to d upper y, the colors not belonging to d upper y, do not intersect. They lie in the complement.
Yes, I know. Continue the proof of lemma y.
Mm-hmm. Okay, so I'm just thinking either to go on with the proof or to, because I'm not sure that I will be able to prove this lemma. The proof is not so short. Okay, let me try. Maybe 20 minutes is enough. Let me try. Let me try to prove this first lemma. and the next lemmas will follow on the next lecture. Okay, let's start with the proof. So since we are working with a simple spherical variety, we may assume we know it is quasi-projective, so we may assume that X sits in the projective space, which is the projectivization of some V, and V is the linear representation of G, is the space of the linear representation of G. So G acts on the vector space V, and so it acts on the projective space P of V. And X is a G-stable subvariety in this projective space. Since it is quasi-projective, it can be always embedded, equivariantly embedded in the projective space, equipped with the linear action of G. Let us take the projective closure of X in this projective space. So X bar is the projective closure. And we do the usual thing. We do the affinization procedure. So we consider the vector space V lying above this projective space. And in this vector space V, there sits an affine cone X hat. It is the affine cone over X bar. Okay. And in this affine cone X hat, there sits a smaller affine cone. Let me denote it as D X hat. D stands for the boundary cone. It is the cone over the boundary of X in X bar, over X bar minus X. So here is a picture for you. Again, as usual, here is a picture for you. So we have this X in the projective space. We take its closure. So we get X bar. We take the cone over X bar. We take the cone over X bar. This is what I denote X hat. And the boundary is this. The boundary cone, it is this cone. This is dx hat. It is the cone over this guy, which is X bar minus X. Okay, so here is the picture. So let me put the origin of the vector space V here. Okay. Now, since my closed orbit Y, it is closed in X, not in X bar. But since my orbit Y sits in X, it is not contained in the boundary in X bar minus X. So let me draw the orbit Y in the picture here. So here is Y. It is not contained in X bar minus X, and therefore we may again consider the cone over this orbit. But let me now consider the punctured cone. So the cone without the origin. Excuse me. Should draw it better. Let me try. So this is the cone.
All of the cone does not contain origin, right?
No. When I'm considering x hat, I am considering the affine cone. So it is an affine variety. It is closed in V, and it contains origin. X hat contains origin. Let me write it here. So this guy contains origin. This guy also contains origin. But as for the cone over Y, I don't want it to contain origin. So this Y hat will be this guy without origin. Without origin. So let me put an arrow here. We do not take the origin here. But anyway, we may consider the vanishing ideal of this cone in the coordinate algebra of the cone x hat. So let's consider the coordinate algebra of the cone x hat, and the vanishing ideal of y hat, all polynomials vanishing on this y hat inside this coordinate algebra. As you see from the picture or from the formula, these two cones, the red one and the green one, are not contained in each other. So what is important for us that y hat is not contained in dx hat. So the green cone is not contained in the red cone. And this implies that the vanishing ideal of y hat does not contain the vanishing ideal of dx hat. So there exist functions which vanish on y hat but do not vanish on x hat. Okay. This means so is it what I need? Let me think a while. So y is not contained in here, and for vanishing ideals the opposite inclusion doesn't hold. Yes. So this means that we may decompose this ideal, the vanishing ideal of the boundary cone dx hat, as the direct sum of the intersection of these two ideals. So this would be the vanishing ideal of the union y and dx hat. And some complementary G-stable subspace M, which is even G hat stable, because on the vector space V there acts a bigger group G and one-dimensional torus of scalar operators. So this G hat is also reductive, and this complementary subspace can be chosen to be G hat stable because of complete reducibility. G hat stable subspace. Okay, so we choose this G hat stable subspace, and now choose a polynomial, a non-zero polynomial in this G hat stable subspace, which is an eigenvector for the Borel subgroup for B hat. Since this subspace M is G hat stable, then we can choose a highest weight vector in it. So we can choose such a polynomial. It is homogeneous. It is homogeneous because it is stable under the scalar operators. This subgroup B hat includes scalar operators acting on V, and any polynomial which is an eigenvector for scalar operators is homogeneous. Okay, so it is a homogeneous polynomial, and we can consider an open subset in X let me denote it X upper knot, an open subset in X, maybe, yeah, an open subset in X.
Professor,
Mhm.
I think F should not be considered as a polynomial because the coordinate ring on X hat is not a polynomial, but the quotient of the polynomial.
Well, I mean, it is a polynomial on X hat. Of course, it is a polynomial on X hat, which means it is.
So how can we define homogeneity on X hat?
Because X hat is a cone. X hat is stable under scalar operators, and the vanishing ideal of this cone is homogeneous.
Just means that it is semi-invariant under the scalar multiplication.
Exactly. So you may say that a homogeneous is the same as coming from a homogeneous polynomial on the whole vector space V, because the vanishing ideal of X hat is homogeneous. Since X hat is stable under scalar operators, the vanishing ideal of X hat is homogeneous. And this means that any homogeneous element of the coordinate algebra of X hat comes from a homogeneous polynomial on the whole V. So you may consider homogeneity in any sense. It is compatible. So let us denote by X upper knot the non-vanishing locus of this polynomial f in the projective variety X bar. Of course, f is not a function on X bar. F is a function on X hat, but coordinates on X hat can be considered as projective coordinates on X bar. And this function f is homogeneous. So it makes sense to speak about vanishing or non-vanishing. So I'm interested in non-vanishing locus. About vanishing or non-vanishing of a homogeneous form in projective coordinates at a point on the projective variety. So this X naught will be an open subset. It will be a B-stable open subset, B-stable, affine open subset in X bar containing X contained in X, because this F vanishes on the boundary of X bar. Yeah, by construction, this F is in the vanishing ideal of the boundary cone, so it vanishes on the boundary of X bar. This means that the non-vanishing locus is contained in X. And also it intersects the orbit Y.
Professor, why is it affine?
It is affine because it is defined as a non-vanishing locus of a homogeneous form on a projective variety, just by projective geometry. When you take a projective variety, and when you take a homogeneous form in projective coordinates, and take the non-vanishing locus of this form, it will be automatically affine. Okay.
So even if the projective variety is not smooth, the non-vanishing locus.
It is not about smoothness. Doesn't matter here. So essentially, when you take a homogeneous form, you may consider say if you take a homogeneous form of degree d, you can consider the vanishing locus, the hypersurface defined by this homogeneous form, can be considered as the hyperplane section under the default embedding of this projective.
I know that.
Okay, and when you take off the hyperplane section, then what is left is an affine open subset. Okay.
Okay.
Okay. Okay. So, and finally, this open subset intersects the open orbit Y. Because this F is taken from M, elements of M are, do not belong to the vanishing ideal of Y hat, okay? Elements of M do not vanish identically on Y. So this is because of our choice, of this homogeneous form F. So we found an affine bistable open neighborhood of Y. So let me recall that.
Y. So X naught should contain Y naught.
No, X naught does not contain Y. X naught intersects Y. X naught just intersects Y. Some pieces of Y can be outside.
Intersects Y.
Yeah. The only thing I claim is that X naught intersects Y. So what we have done, we have found an affine bistable open subset of X intersecting the orbit Y. Now let's take any such open subset. So let me turn to the next step of the proof. So let us take any bistable affine open subset X naught in X intersecting with Y. The one we constructed on the previous page or any other open subset, it doesn't matter. So if you have such an affine open subset, then we know that the complement of this open subset in X is a union of finitely many prime divisors. We have proved such a lemma some time ago. So these divisors are, of course, bistable, but not G-stable, because all G-stable divisors contain Y, since X is simple. So these divisors Di are colors not containing Y. So they are colors in the complement of this subset D over Y. Okay? But maybe it is not the whole subset. Not all divisors in this subset occur among this D1, DS. Let me also add all other colors in this subset. So let me denote this subset of colors not containing Y as D1, etc., DT, where T is greater or equal than S. So some of these colors are in the complement of X naught, but maybe there are other colors which intersect X naught. So the picture is like this. Again, we have X. We have X. We have the closed orbit Y in X. This is Y. We have the open affine bistable open subset X naught. We have colors in the complement of this open subset. Say, well, I mean, say this one. Excuse me. The colors in the complement of this open subset, these are this D1, DS. Of course, they do not intersect. They do not contain Y. But we also may have some other colors. What color is left? Maybe, I don't know. Maybe just black. We may have some other colors, DJ, with J greater than S. which may intersect. Which may intersect. Let me draw it like this. Which may intersect this open subset. Okay. And if we want excuse me, to pass to this x y naught hat x y naught, if we want to pass to this x y naught, then we have to remove these colors from the picture. We have to remove the colors dj from x naught, and what will be left? It will be xy naught. Now we want to show that we can that removing these colors will give us an affine open subset. But I see that my time is over, and
well, we require that xy naught is affine. I don't think the theorem tells us that xy naught is affine.
We have to prove it. So we have to prove that xy naught is affine.
I think.
So we didn't yet prove it. We have to prove it. But unfortunately, I have no time to do it now. So I have to postpone finishing the proof of lemma 1 for the next lecture for Wednesday. And now I think I have to stop. Sorry, now I see that it would be better to postpone the whole proof of lemma 1, because it is not a good idea to break the proof in the middle, because at the beginning of the next lecture we have to remember to recall what was done in the proof before. But anyway, so my time is over, so I have to stop now.
So next lecture is Wednesday or next Monday?
Next lecture is Wednesday. Yes, next lecture is Wednesday. On Wednesday we shall finish the proof of this lemma. Next we'll prove some more lemmas about this data, about these two subsets, v over y and d over y. And then we formulate and maybe prove in part the theorem, the classification theorem on simple spherical varieties. Okay, this is the plan for the lecture on Wednesday.
Professor, I have a question. So you mean that the complement of a hypersurface in a projective of variety is always affine?
Yes, of course.
But
if your hypersurface is given by a single equation, if you understand by hypersurface not just a codimension one subvariety, but a subvariety given by a single equation, then the complement will be affine.
I know. I have a side question about the classification problem.
Yes.
So, would it be easier if we restrict our X to be complete variety?
No, actually not. You will see how to distinguish complete varieties among all spherical varieties from the classification. But to handle the classification, the complete case is not easier. It is equally. It is of equal complexity, I would say. Of course, in the course of proofs, sometimes you pass, as you have already seen, sometimes you pass to projective closure or whatever. So sometimes you compactify. But eventually, the answer will be not easier, and the proof for this answer to classification problem will be not easier in the complete case than in general case.
Oh, I know.
But the complete case will be distinguished, of course, and you will see what is the condition of completeness in terms of the data classifying spherical varieties. Okay. So, are there more questions? It seems that there are no more questions. Well, then maybe.
I mean, the complement of a hypersurface given by a single equation. You mean can be seen as the hyperplane section of the degree D varieties map to some higher dimensional projective space, right?
Absolutely, absolutely. It is given by the Veronese map. Yes.
But the Veronese map does not necessarily maps the projective variety X into some nice space. I mean, if X itself is of codimension more than one, the Veronese map will map X into I would describe it as curved, some curved variety, not linear sub-variety.
Well, of course, X itself will be some small subvariety in a big projective space. But when you take its hyperplane section, you get a hypersurface in X. So yes. the point is
the complement of the hypersurface in the large projective space is the subvariety of a large affine variety. I see.
Yes. So this is all these are standard things from projective geometry. Of course, if you come to the things for the first time, this may be puzzling, but actually this is not that complicated. It is indeed done by Veronese map. More questions? So let me say that now we indeed come to some technical part of my course, because the classification theorems for spherical varieties, well, they are formulated easily, which you will see soon, but the proofs are not so easy. The proofs are quite technical. So we now go into technical part of the course, and you have to be a bit patient. If you want to get the proofs, you have to go through these technicalities. But after the theorems are proven, you can use them more or less forgetting about the proofs, I would say. For applications, these technicalities are not that necessary. But anyway, if you want to prove the theorems, then we have to prove technical lemmas. So I'm sorry for that, but it is inevitable. Okay, so more questions, comments, whatever. Well, if not, let me stop sharing the whiteboard. And I hope to see you on Wednesday on the next lecture. Thank you for your attention and goodbye.